Hello, today we are going to start with Lesson 5, which corresponds to Gauss's Law. This lesson, we have structured it in 5 classes. In the first class today, we are going to see an introduction in which we are going to explain the concept of flux. In the second class, Gauss's Law will be stated, and then there will be 3 lectures in which we will do problems, in which we will apply Gauss's Law to calculate the electric field created by linear charge distributions, surface distributions, and volumetric distributions. So let's start with the introduction. Let's look at the concept of flux. The electric field flux through a surface S is a scalar quantity that tells us the amount of field that passes through that surface. The mathematical expression of this quantity is the one we see on the screen. It corresponds to the surface integral of the scalar product between the electric field and differential vectors of S. But let's see how to arrive at this expression. For this, we will define the elementary flux of the electric field through an elementary differential surface of S. Let us choose any surfaces. Let's mark a differential of area. And the central point P, at this point we will first evaluate the electric field. We will see how much is the electric field at this point, and we will represent it with its corresponding vector. Then we will evaluate the differential vector of S, which is a vector whose module corresponds to the area of this differential element and is perpendicular to the surface at that point. Well, the elementary flux of the electric field through this area differential is equal to the scalar product of these 2 vectors and differential of S. Therefore, it is the product of the modulus by the cosine of the angle they form. To calculate the total electric field flux through the entire surface S, we have to do the same in the infinite elements that compose it. That sum of infinite terms corresponds to the concept of surface integral that we see in the definition of flux. As the electric field is measured in volts divided by meter and the differential of S in square meters, the units of measurement of the flux are volts per meter. Let's look at an example. Let's calculate the electric field flux of 10 volts meter through the rectangular surface shown in the figure, the yellow-sided surface, a rectangular surface of sides A and B. It is a constant vertical upward electric field of modulus 10. The procedure is as follows. We first choose a generic point on the surface in question. It is going to be a point with x and y coordinates, and the z coordinate is always going to be 0, since the surface is in the z plane equal to 0. Then we evaluate the electric field at this point. In this case, is constant and therefore worth 10K. Then we calculate the differential of S also at this point is equal to the differential modulus of S times the unit vector K, since it has to be a vector perpendicular to the surface. Therefore, we see that we have 2 vectors, E and differential of S, that are parallel to each other. By performing the scalar product, therefore, we have the product of their modulus. If we substitute this result into the integral of the definition, we get the following result. We see that we have the integral of 10 differential of S. The 10 is constant comes out. I get the surface integral of differential of S, which is equal to the area of the surface in question, that is LA times B. Then the result of this problem, the electric field flux 10K across this yellow surface is 10 times A times B. Let's look at a second example, in which we are going to calculate this time the electric field flux created by a positive point charge located at the origin of coordinates, and we are going to calculate it through the spherical surface of radius r capital shown in the figure. We will follow the same steps as before. First, we choose a generic point on the surface P, and on it we are going to evaluate both the electric field and the differential vector of S. The electric field created by a positive point charge at a distance r capital R from it is K times the value of the charge Q divided by the distance r capital squared by the unit vector U sub R. It is a unit vector in the radial direction. The differential vector of S is also the differential modulus of S times this unit vector U sub R, since the differential vector of S has to be perpendicular to the surface and outward. Therefore, in this case, the electric field vector and the differential vector of S are again parallel, their scalar product being equal to the product of the modulus. If we substitute this result in the integral of the definition, we get this expression. We get the integral of something that is constant, which can go outside the integral, and then we are left with the surface integral of the differential of S, which is equal to the area of that spherical surface we have chosen of radius r. That is 4 pi r squared. Doing the appropriate operations, we see that it is equal to the value of the charge q divided by the electric permittivity in vacuum epsilon sub 0. Emphasize that the flux, the result, we see that it is equal to the charge enclosed by that surface divided by the electric permittivity in vacuum, epsilon sub 0. Result that coincides with Gauss's law, which we will see in the next class. And that's all. Thank you very much for your attention, and see you next day.